It's a real pleasure to introduce Chris Field today. I boiled everything down to a single page, but it's very small font, and that was a real challenge to get all on paper to try to figure out exactly how I could introduce somebody with so many accolades and actually so many different titles. To tell you how accomplished he is, it's just, you look through the list of all the different things that he is the head of, so to speak. So he's director of the Carnegie Institute's Department of Global Ecology. He's also the Melvin and Joan Professor of Interdisciplinary Environmental Sciences here at Stanford. He has two departments that he represents, both biology and environmental earth system science. He's the faculty director of Stanford's Jasper Ridge Biological Preserve. And then a big part, I think everybody knows this, he's the co-chair of Working Group 2 for the IPCC. Any one of those is a full-time job, and yet he manages to do all of those at the same time. And it wasn't that long ago, I think it was last year or so, that it hit me that he does all that while he spends, maybe 90% of his time, at least during those years, on a plane. And I think at least for a few years, he was logging more miles in 1 year than I will in a lifetime, or at least that I want to in a lifetime. And I had a trip to South Asia that I was there at the same time that Chris was there. And we were there about the same duration, and we came back. And a couple of days after that, I thought, God, I'm exhausted. I'm finally getting my strength back. And I realized he was getting on another plane and heading off to Brussels, and that wasn't the uncommon transition for him to do. So anyways, it's pretty amazing that he's able to do all those things. Not surprisingly, he's got a tremendous number of accolades as well. Wasn't that long ago, he was the recipient of the Heinz Award, which I particularly enjoyed congratulating him about. Not every day that you get to talk about ketchup, but anyways, he's also a member of the National Academy of Sciences. He's a fellow in a number of different associations, the American Academy of Arts and Sciences, the American Association for the Advancement of Sciences, and the Ecological Society of America. The number of different things that Chris does is also really staggering in terms of his research, not just interests, but the depth that he goes into. I could go into those expansively, talk about nutrient cycling, ecology. Obviously, the biggest part that we're going to hear about today is on the climate science. And so Chris has been one of the leaders in the climate field, particularly from the terrestrial and ecosystem science side of the equation for many decades now. And his research is really tremendous. It's why he has all those accolades in there and why he's so respected within the IPCC. So with that, I'll turn it over to Chris and let him take off.
Thanks, Scott. The secret of having lots of titles is that you can always say you were working on the other one when people were looking for you. Well, thanks very much for the introduction. Looking forward to sharing some thoughts with you today. My main topic is the most recent special report from the IPCC, which is focused on managing the risks of extreme events and disasters, which is where I think the real action in climate science is. But before doing that, I want to share a series of myths about climate change and one important fact that's really changed the climate landscape. It's a fact that I think many people in the climate science community are only beginning to realize how powerful it is. The myths I want to talk about are mainly myths that are perpetrated by the green side of the climate science, climate advocacy perspective. And in many cases, these myths are beginning to create real problems for understanding the landscape and the dimensions of the path forward for action on climate change. Okay. Guess that doesn't work. So I want to talk about three kinds of myths. Myths about the nature of climate impacts, myths about the timing of the impacts and the responses, and myths about the role of science in decision making and what we can expect with future discoveries. And I also want to talk about a new way to conceptualize the problem of when we need to act to stabilize climate at 2 degrees or any other target. And there's really new information that dramatically simplifies the way we think about this. It dramatically complicates the set of actions that are available to us. I want to talk about 3 myths that are related to the nature of climate impacts. And I'll read through these now and then talk in some detail about each one. So the first myth is that the impacts of climate change are mainly connected to average conditions. That once we see the averages, we'll see the impacts coming out clearly as a consequence. The second myth I want to talk about is that vulnerability to impacts is concentrated, especially in communities that are poor, lack advanced infrastructure, or have ineffective governance. That climate change is really about them. It's about poor people in Bangladesh, and it's not about people in the developed countries or the rich in the world. The third myth I want to talk about is the idea that's sort of the foundation of the Cancun Agreement. It's the idea that limiting the increase in global average temperatures to 2 degrees centigrade over pre-industrial represents kind of a guardrail, that we don't need to worry about, as the UNFCCC characterizes it, dangerous anthropogenic interference in the climate system if we can limit the warming to less than that. The two myths that I want to talk about in the context of the timing of the impact and responses is that first, that near-term investments in mitigation will yield benefits in decreased impacts. One of the big challenges we face in thinking about investments is when we're going to see those investments pay off. And the timing really represents a challenge. The other myth I want to talk about in the area of the timing and the magnitude is a myth that it has different flavors that are perpetrated by the skeptics community and by the green community. And it's basically the myth that if we can't stabilize warming at 2°C, then there's almost no point. We've sort of lost the game. And the skeptic interpretation as well, there's no point in investing. And the green interpretation is that there's such a high risk of going over some kind of a tipping point or threshold that we absolutely, positively need to make sure that we don't pass that 2-degree guardrail. And then the final myth that I want to talk about just for a couple of minutes is about the role of science. And essentially, you can state this myth as saying that additional research will facilitate smart decision making by reducing the uncertainty in the severity, timing, and spatial pattern of the impacts. The bottom line is that in some cases that's true, but in others it really isn't. And we need to recognize where the limits of the science are in the short and the long term. So I'm going to spend most of the talk focusing on this question of the impacts of climate change and the way they play out in the balance between average conditions and climate extremes. That was essentially the core elements of this IPCC special report that I'll make the focus of the second half of the talk. Okay, the second myth I want to talk about is this one about where the concentration of vulnerability is. And there's no question that if you look at the traditional definitions of vulnerability, that vulnerability is concentrated in poor communities, where there's poor governance or where there's lack of access to the kinds of resources that can be deployed to solve problems. Here's a ranking of a vulnerability index for a bunch of countries in South and Central America, and it's really clear that poor countries have higher vulnerability. But then on the other hand, if you ask, well, what's the full range of consequences of especially climate-related extremes and how do those play out across regions, what you see is that there's this big mismatch where there are lots of extreme events. The stacked bar here is the number of climate-related disasters. This is from 2000 to 2008. And the black bar is the economic losses in billions of dollars. And what you see is that there are climate-related disasters all over the world, but the economic disasters are concentrated in the developed regions, in the developed parts of Asia, Europe, and the Americas. And the consequence is that the effects of climate-related extremes and disasters play out primarily in economic losses in the world's developed regions, and they play out in loss of lives, loss of future opportunities in the developing regions. But there's not a sense in which there are real impacts in one place and not real impacts in other places. They're just different kinds of impacts. And when we think about vulnerability, we just need to recognize that there are different flavors of vulnerability, and each of us can bring our values to the aspects of vulnerability we consider most important, but we wouldn't want to ignore the financial impacts just as we wouldn't want to ignore the impacts on loss of life. The myth about the 2-degree guardrail is really, really challenging. The 2-degree guardrail concept has essentially been the flag under which the UNFCCC has marched ever since the 2010 Cancun Agreement. And it's really challenging for several reasons. One, we have already witnessed widespread, comprehensive consequences of climate change. No question about it. Are those dangerous anthropogenic interference in the climate system? You know, it depends on whether your home was destroyed or your family lost its business. There are thousands of people in parts of the world that have been impacted. So this question of dangerous anthropogenic interference isn't really a yes-no question, it's a question of scale. What's the scale at which dangerous anthropogenic interference is widespread enough that it passes the threshold defined by your values or my values? If we look at the evidence for the kinds of climate impacts that have already had clear events, at least to me, I think the clearest signals come in the relatively new science of single event attribution. If you ever hear a climate scientist talk about a single extreme event, the first statement out of the mouth essentially, well, we can never 100% certainty attribute a single event to climate change or not. But there's a very rich field of science now that is evaluating the odds that a certain event occurred under an environment with the full range of climate forcings, including the human ones, and without those. And if you look at the single event attribution analysis of a number of recent extremes, including extremes that have led to tens of thousands of lives, like this European heat wave of 2003, billions of dollars of lost income, the UK floods of 2000, or the Texas-Oklahoma heat wave of 2011. In each of these cases, the single event attribution indicates that the odds of that event occurring have increased substantially as a result of human-caused interference in the climate system. In the case of the European heat wave, there's at least a 90% probability that the odds were at least twice as high that that event would occur in the environment of the 2000s and in the mid-20th century. In the Texas-Oklahoma heat wave of 2011, the odds had increased 20-fold of having a profound heat wave relative to the conditions in the middle of the 20th century. I think there's no question that we're seeing consequential, widespread impacts. It makes this issue of dangerous anthropogenic interference a lot more subtle and interesting, but I think it also presents the challenging possibility that we've already passed the threshold of dangerous anthropogenic interference, which makes it really tough to figure out what we're going to do with the UN Framework Convention, where Article 2 says the goal of this treaty is to prevent dangerous anthropogenic interference. A third really challenging myth that I want to talk about is this, the concept that near-term investments in mitigation will yield near-term investments in impacts. It's not true. Essentially, if we're dealing with a climate system in which decades of future changes are really baked into the system. Some of these are a consequence of heat that's already been stored in the atmosphere and oceans. Some of the changes that are baked into the system are consequences of the infrastructure that we can't retire tomorrow. And some of the consequences are baked into our mindsets and the governance and institutional environment in which we work. If you want to see the consequences of that, a good way to do it is to compare, here's the end of the century warming. This is from the 2007 IPCC report. For A1T, this is the high-tech, high economic growth scenario, yields end of century warming anywhere from about 1 to about 3C with the A1 fossil intensive. And what you can see is that they overlap broadly. And if you look at the trajectories here, you can think of the uncertainty range surrounding each of these scenarios as the light color. And let's compare A2, sort of a burn the fossil fuel as fast as you can scenario, with B1, which is a kind of a boutique, everybody does their own thing, high-tech approach. And what you can see is that B1 and A2 do separate from each other. It's where the light-colored bands begin to diverge. But this point of separation is somewhere around 2050. So what this is saying is that based on the analysis in the IPCC AR4, you wouldn't expect the consequences of an investment in mitigation to be visible in the global average temperatures until about the middle of the century. If you look at a specific region, the challenge of doing the separation is even greater. Here's an analysis from the new CMIP5 database, thanks to Dahi Stone, for the United States, comparing the burn the fossil fuel as fast as you can scenario, RCP 8.5, with a pretty aggressive mitigation one, RCP 4, and you can see that the temperature uncertainty for the US basically overlaps through the whole century, and you would be surprised if even by the middle of the century you could detect with any level of confidence that you actually were seeing effects of investments in mitigation. At least for me, that means we really need to think about the next century, the coming century, as having two really importantly distinctive eras. The first I like to call the era of climate responsibility. That's the era during which we need to accept responsibility for the fact that we have got ourselves a bunch of problems associated with climate change, and that whatever we do over those decades is not going to produce clear consequences during that period. But it's an era of climate responsibility in two important senses. One sense of importance is that we're responsible for the changes we've already baked into the system, but it's also a period during which we have responsibility for influencing the conditions during the second half of the century and periods after that. So we need to recognize that investments are really important, but they're important for consequences that are going to appear in future decades. The second half of the century and beyond is an era I like to call the era of climate options, and that's the time frame during which investments are actually going to make a difference. Investments then will make a difference as well. But until we can really crisply separate what our goals are and what our strategies are for the era of climate responsibility and the era of climate options, we're going to have some real problems. And in particular, it's not realistic to base advocacy for climate change on the idea that investments now are going to result in short-term improvements in the state of the climate. The next myth I want to talk about is this, the myth that if we can't stabilize warming at 2°C, then there's no point investing in stabilization. There are a whole bunch of arguments about why this myth is incorrect as stated, and the simple answer for me is that the longer we wait to do anything about climate, the more residual impacts we end up with, the more complication we face in dealing with the climate changes, and the more it costs. In terms of a picture, I think this image from a new paper by Noah Diffenbaugh and Filippo Giorgi is really compelling. So this is the graphical evidence that a world with, this is slightly less than 4°C of warming, is getting pretty close to unrecognizable. So what they did for this analysis, which just came out in Climatic Change, is they compared the highest forcing of the new IPCC scenarios, called RCP 8.5, for the end of the century, and compared it to 1986-2005. It's a global average warming of 3.8°C. And then they said, what's the fraction of the summers that are warmer than the warmest summer during 1986 to 2005. So if it's this dark red, which almost all the world is, it's 100% of the summers are warmer than the warmest summer in the observational period. And what you can see is that, essentially everywhere, unless you happen to go to the North Atlantic or to northeastern Argentina here, are hotter than the hottest period in the record 100% of the time. It really is a world that is unrecognizable. And it also is the case that we tend to stop our analyses at the end of the 21st century because we kind of run out of computer power. But this warming continues with something like RCP 8.5. And we're not only looking at a world at the end of the century that's different than anything we see now, but we're on a trajectory of very, very steep warming. Okay, the final myth I want to talk about is the myth that well, we really shouldn't do anything now because additional research is going to clarify the problem to the extent that it'll be obvious what we should do next. And I think the question of the intrinsic sensitivity of the climate to increasing CO2 provides a really useful format for looking at this issue. So this is a probability density function for equilibrium climate sensitivity for a whole bunch, every published study that we could find in this study. And you can translate directly from the equilibrium climate sensitivity to the CO2 concentration that gives you 2 degrees of warming. So if the equilibrium climate sensitivity, how much warming do you get from a doubling of CO2 over pre-industrial, is 8 degrees, a really high number, we've already passed enough CO2 concentration to get us to 2 degrees of warming. If it's only 2 degrees, we can go up to something like 500 parts per million before we get 2 degrees in the system. And so what you would like to see is that as time moves on, this probability density function gets narrower and narrower, and we learn more and more and are able to say with more and more precision where we're headed in terms of climate forcing. But what you see is that there's no historical trend at all in the width of this probability density function. The new studies are just as broad as the old ones, and there's actually no reason to think that further progress in science is going to significantly narrow this PDF. Some of the new studies have actually concluded that mechanisms that hadn't been given their full weight are more important than expected. As new kinds of paleoclimate sources have been brought in, some have resulted in narrower distributions and some have resulted in wider distributions. But it's really clear that new research isn't going to solve the problem. What we need is a decision environment in which we could recognize that this is the state of the science. Some things are going to improve, but others aren't. And I want to talk just a little bit about that in the context of a particular piece of information that's emerging from the new climate analysis. And to do that, I want to say just a couple of things about the essence of risk. You know, climate change is really a challenge in managing risk. And what is risk? In the formal sense, it's often useful to think of risk as the product of the probability of some event happening and its consequence. And with most things in the physical world, and certainly with climate change, we are very fortunate if we can characterize the future in terms of a probability density function, one like this, where there's some range of possible outcomes and we can associate a probability with each. With climate change, typically as we go to larger and larger amounts of forcing, we're going to be looking at larger, more consequential impacts. And so we might have an environment in which for this probability density function, we'd be having consequences that go up like that. And the product of those is something that doesn't center on the center of the probability density function, which is where we really have focused most of the research in climate science. The product of those is shifted off to the right as a consequence of this steeply rising trajectory for the impacts. Now, I've drawn the trajectory for the consequences as if that also isn't associated with some statistical uncertainty. Of course it is, and you end up with a complicated multidimensional probability density function if you have it, but it's almost always one where if you do the integral or if you ask about the parts of the domain that you care the most about, they're shifted off to the right, to the higher impact, lower probability side of the probability space. One of the interesting consequences of having risk be the product of probability and consequence is that if you know less about the probability density function, the motivation for investing in solutions is often higher. So for this example, what I've done is just squished out the probability density function, sort of what we know about most kinds of impacts. And in that case, what happens is that the risk, shown here in the green, really takes off because now this more of the probability is off in the right-hand side. And if you were a risk manager and you were able to say, well, how much should I worry about this probability density function versus this one, the risk is a lot higher from this one, and you really would be investing more if you were trying to manage the full set of possible outcomes. And in general, you know, knowing less means you should invest more, at least in the climate space. So now I want to go to another new kind of development in climate science, This is a really terrific figure that Noah Diffenbaugh just drafted. And it provides more information than I've seen about future precipitation estimates than any other one. So they're basically 4 things that this figure shows. The white areas are areas where, this is for the end of the century with this burn all the fossil fuels you can get scenario, RCP 8.5. The white areas mean that the climate models basically aren't showing a change in precipitation, that the precipitation hasn't emerged from 2 standard deviations of the normal trajectory. The gray areas, which includes a lot of really important parts of the world, are areas where the amount of precipitation change has emerged from the background noise, more than 2 standard deviations away from the background noise, but the models don't agree on the sign. It could increase, we're pretty sure it's going to change, but we don't know what direction. And so if you live in, most of South America, parts of sub-Saharan Africa, the central US, and quite a lot of the South Pacific, you're in an environment where, as a risk manager, you're saying, okay, I have new information that there are going to be consequential changes, and I need to figure out a way to deal with that, recognizing that I don't even know the sign of the change. It's a really hard problem, but it's the nature of the problem. Just to finish out what's in this figure, the areas that are a color with the white stippling are areas where at least 2/3 of the models do agree on the fact that there's a change and on the sign of the change. And then the white stippling disappears when at least 90% of the models disappear on both the magnitude of the change and the sign of the change. And so what you really see is that even for this quite extreme scenario, it's not that much of the world where we can project with any level of confidence what the precipitation changes are likely to be. Okay, that's what I want to do on climate myths. Anybody have a question on climate myths? Okay, well, I know nobody here would ever perpetrate any of them, so I feel comfortable moving on. And I want to talk about a fact, and an amazing simplification in climate science has emerged recently. And if you look across all the models, what you see is that the amount of peak warming from CO2 release is almost linear with the cumulative amount of CO2 that's released. For most models, it's around a trillion tons of carbon released to the atmosphere gets you 2C of warming. 2 trillion gets you 4C. We've released just over 500 billion tons of carbon to the atmosphere as a consequence of fossil fuel combustion to date. It's a nice kind of exploration of this concept in a paper in Science that just came out a couple of weeks ago. It's by Thomas Stalker, who's the co-chair of Working Group 1 of the IPCC. And it really is an organizing theme for the next IPCC report that you'll see. And what this plot shows is the stabilization target over pre-industrial, and the starting year of emissions reductions, and the rate of emissions reductions. The assumption here is that you're doing these rates of emissions reductions from an intrinsic growth rate in emissions of 1.8% per year, and this one's assuming that the climate sensitivity is 2C per trillion tons. And what you see is that if you could decrease emissions by 5% per year, incredibly aggressive in the context of the way people think about the economics of emissions reductions, that if you wanted to hit 1.5 degree target, you might be able to do it if you started now, but you'd really need to start by Thursday. If you're talking about a 2 degree target and you could reduce emissions at 5% per year, you'd be looking at needing to start by the early 2030s. If a more realistic approach was that you could only reduce emissions 1.5% per year, we're right at the limit of whether 2 degrees is achievable. Well, 2.5 degrees is achievable now, 2 degrees probably is not. And really strikingly, unless you have ways to remove CO2 from the atmosphere, we have already passed the point at which 1.3 is baked into the system, and we're quickly closing the door so that no matter how fast we could remove, if we didn't do anything till 2040, we passed the 1.5. Not doing anything till 2060, we passed about 2.5. It's really simple, but this is a terrifying figure, because these rates of emissions reductions are really ambitious. You've got to remember that those aren't the rates at which we would reduce emissions at the scale of the US. Those are the global emissions reductions rates. And when we look at the current environment, which is one, well, with the natural gas boom, it's been one of gradually decreasing emissions in the US and rapidly increasing emissions in much of the developing world. We're talking very, very big changes. To even get 1% per year reductions, we've been in a global environment with about 2% per year increases in carbon emissions. Here's another way to think about this closing door, and this shows the consequences of having the climate sensitivity be 1 degree per trillion tons, 2 degrees per trillion tons, or 3 degrees per trillion tons of carbon. And the example I already showed you was for this 2 degrees. This shows for 1.8 per year percent intrinsic growth and 1.5% per year intrinsic growth in the dashed lines. And you can see that if the climate sensitivity is higher, which was certainly compatible with the PDFs I showed you earlier, we've already reached the point at which 1.5 really is not accessible, and rapidly past the point at which 2 degrees is accessible. And this represents the absolute limit if we could go from current emissions to no emissions immediately. On the other hand, if the sensitivity does turn out to be 1 degree per trillion tons, wait a long time. There are several things that are interesting and important about this. One is that it really highlights the power of having technologies that can remove CO2 from the atmosphere. And I'm not going to talk about carbon dioxide removal, but the game would really change if we had techniques for removing CO2 from the atmosphere. It also speaks compellingly to the need for global agreements. Until we can figure out ways to do global reductions in CO2 emissions, we're not going to make the kind of progress that we need to on the scale of the problem. And the third thing it really highlights is the negative consequences of having some kind of delayed participation. We'll start this year, the Europeans will come in a few years, the Chinese will come in a few years after that. The delays really kill you in terms of how big the emissions reductions in the short term are. Okay, any questions on my fact? Okay, so now you know everything you need to know in order to understand the new IPCC report, which is what I want to talk about for the second half of my comments. And I think most of you probably know what the IPCC is. Though the way I think about the Intergovernmental Panel on Climate Change is that it's a negotiated agreement between the world's governments and the scientific community. The world's governments said, if you, scientific community, will follow our rules, we will regard your assessments as the definitive statements on what's known and what's not known about climate science. And their rules were essentially these three. It has to be a comprehensive assessment. You can't pick the things that you want to talk about. There have to be multiple layers of monitored review. The draft reports are available for review by anyone who wants to provide review comments. The rules are that every scientific comment has to be responded to, and there's an independent group separate from the authors who make sure that they are responded to. Just by way of advertisement, the second order draft of the Working Group 2 report becomes available March 28th, and I'm going to be disappointed if I don't see review comments from all of you. One of the really nice things about the review environment is that all you have to do to be an expert reviewer is provide a scientifically based review comment. It's not like you need a degree or an anti-degree. And then the really interesting thing about the IPCC process is that the summary for policymakers, the little 20-page documents that most of you have probably seen, they're approved word by word, by consensus, by all the governments in the world. And so if we were doing plenary approval of a summary for policymakers and I was chairing it, I would say, okay, The first sentence of my summary for policymakers is warming in the climate system is unequivocal. I would put that up on the whiteboard, and you guys would be the representatives of all the countries, and I'd say, does everyone agree that this represents the definitive statement of what's known and what's not known about the science? And we wouldn't move off of that statement until every one of you thought that that was the accurate characterization of the state of the science. And I know it's amazing that the summaries for policymakers are longer than one line, but they are, and at least to me, it speaks really compellingly about two things. One about the value of peer pressure and how countries can force each other to get along. I try to convince myself that it doesn't say very much about the irrelevance of the science to the policy-making process within the countries, but that's a topic for another day. But it also says that the process of getting countries to agree to follow a set of rules really does work, at least in the environment of figuring out what the science says. So with that as background, in about a year ago, March of 2012, we released the IPCC special report on managing the risks of extreme events and disasters to advance climate change adaptation. It was the first time the IPCC ever tackled extreme events and disasters. And to do that, we assembled a multidisciplinary, multi-working group team. It included Working Group 1, the people who work on the physical aspects of climate science, included Working Group 2, the people who work on impacts, adaptation, and vulnerability, and it included a lot of representatives of the disaster risk reduction community, the UN International Strategy for Disaster Reduction, the International Red Cross, the people who really have to deal with disasters. And it was really interesting and informative for everybody who was involved to understand how different perspectives on not only disasters were, but on the best approaches to dealing with them. The starting point for the special report on extreme events and disasters was really based in the IPCC fourth assessment report, the 2007 report, and it was a conclusion that a changing climate leads to changes in extreme weather and climate events. It's actually a really important statement, and it helps move toward this richer understanding that I started out with about how much of the impacts of climate change really come through the extremes. Just to summarize really quickly, there are kind of three take-home messages from the report, and everybody needs to leave. They can leave right after I get through this slide. The first major conclusion is that we've already seen increases in several kinds of climate-related extremes. I'll go into detail into what those are. We also have seen increases in damages, in economic damages from extremes, but that's a relatively narrow window on what kinds of impacts there have been. And at least the statistical analysis that we have now says that the main source of this increase in economic losses is from increased exposure and increase in the amount of stuff, the buildings, infrastructure, people, but not lives, who are in harm's way. And then the third, and in many ways, for me, the most satisfying part of the report was the work on what you might think of as a solution space and the dimensions of the solution space. And the conclusion is that a wide range of solutions can help decrease disaster losses while also contributing to sustainable development. And in general, in the sustainable development world, the kinds of things we're looking for are low regrets investments where you have multiple beneficial consequences from doing things that you should be doing anyhow. In some ways, it's really obvious that a small shift in climate should lead to a change in extreme events. Here's a hypothetical example where we've got some kind of a PDF of an existing climate with a solid line and an altered one in the dashed line. We've just taken the same PDF and shifted a little bit to the right. And what you see is you get a really big increase in the area under the right-hand tail of the curve. If you think of these as extremes and these as kind of super extremes, you get a big increase in the number of extremes, and you go from almost no super extremes to having them be a big part of the package. Of course, there are a lot of other ways that shifts in climate can result in changes in extremes. You can either have a change in the amount of variability, and we're seeing that in many aspects of the climate system, especially with precipitation, or you can have a change in the shape of the PDF, and that can also generate more extremes at one end or the other. And with some kinds of extremes, we're actually seeing more cold extremes and more hot extremes, especially more wet extremes and dry extremes. You can't really understand the way that climate translates into disaster until you have a broader, more socially based view of the nature of a disaster. And in general, you need to think about disaster risk as emerging from the overlap between whatever the triggering event is, the vulnerability, think of it as the intrinsic preparedness of the communities that are at risk, their resilience and opportunities for coping, and the exposure, the amount of assets that are in harm's way. And I think it's useful to think of these as overlapping, with disaster risk kind of emerging from the overlap. In order to really conceptualize the way this overlap plays out in a world with climate change as well as progress on social and economic fronts, it's useful to think about this embedded matrix where we've got climate with both background variability. I don't really like talking about the concept of natural variability because there isn't really anything that's natural about the climate we've got now, and anthropogenic climate change pushing on the dimension of the weather and climate events. And on vulnerability and exposure, we have consequences from development that's not intended to address vulnerability and exposure, and development that is intended to address them directly in disaster risk management and climate change adaptation. The situation is further complicated by the fact, however, that as disaster risk plays out in disaster, it can influence the pathway of development, often severely curtailing development opportunities, especially in poor countries. And whatever the investments in development are, depending on the pathway, has a big influence on the level of greenhouse gas emissions, which feed back to influence climate change. So when Article 2 talks about the goal is to prevent dangerous anthropogenic interference in a way that doesn't curtail sustainable development, you could think of that both as putting an emphasis on the sustainability part, but also on finding a way to manage the greenhouse gas emissions so that you're not doing development at the expense of climate impacts. Given this really rich environment, it's clear that if we want to enhance adaptation to disasters, we can either work on the climate end, more what I talked about in the first part of the presentation, or we can work on the vulnerability and exposure end. And particularly when we're talking about the next few decades, the era of climate responsibility, the real opportunities are mostly at the exposure and vulnerability end of the time dimension and of the problem space. A really challenging aspect of this is that if you look at the history of disasters, there's not a strong one-to-one relationship between the severity of the climate trigger and the severity of the disasters. This cholera outbreak in Zimbabwe is a good example of a real disaster that unfolded as a consequence of very modest triggering events. And if you look around the world, well, the people who come from places like the UN Strategy for Disaster Risk Reduction will often say disasters are a human-constructed phenomenon. They're only modestly moderated by the triggering events. What's happening is climate change is getting to be more important as the relevance of the triggering events is getting to be more important. But you can't just say it's a problem of the magnitude of the triggering events. A really important conclusion, if you look back over the last few decades, is that economic losses from disasters have increased. I told you this was one of the core messages from the report. And what you see is that overall losses and insured losses have both tended to increase. The highest economic losses were in 2005, the year of Hurricane Katrina, which was really the dominant contributor to those economic losses. But the economic loss window is a very narrow window on the climate change problem. It doesn't give you a good information about whether vulnerability is changing. It doesn't give you good information about the components of the environment that are difficult to monetize, aspects of the natural environment, prospects for future opportunities. But if you say, well, what's driven that trend? So far, what appears to be the case is if you correct for changes in exposure, in changes of the amount of assets, infrastructure that were at risk, you no longer see a trend over time suggesting that changes in exposure have probably accounted for most of the increase, but they don't allow you to back out a lot of the things you'd like to back out. Further, it's also really clear that the economic losses are higher in developed countries where there's just more valuable stuff, and a lot of the disaster impacts aren't in developed countries. In fact, if you look at another equally important, or I'd even argue more important, window on disaster losses, what you see is that 95% of the fatalities occur in developing regions where, if you remember back to the map of disaster losses I showed you earlier, the economic losses tend to be really low. They don't have that much stuff of economic value in harm's way. And essentially, in the worldwide map, we see this trade-off between disasters in the developed world play out in economic losses, disasters in the developing world play out in mortality. Okay, I want to spend just a couple minutes talking about the changes that we've actually observed in the climate system and the ones that we project for the future. The historical trend over the last 50 years or so is that there have been clear increases in high temperatures and hot extremes. We've seen those around almost all regions of the world. One of the surprising ones is that there's been an increase in the fraction of rainfall that falls in the heaviest precipitation events. We've seen this both in wet areas and in dry areas, and it's now clear over much of the world. It's especially clear in North America and Europe. Many regions of the world have seen increases in the length or severity of droughts. Some have seen decreases, but the fraction of the Earth that's seen increases in the length or severity of droughts is greater than the fraction that hasn't. And pretty much all coastal regions have seen increases in exposure to storm surge, essentially to the ocean activity that's piled on top of the sea level rise that's already occurred. You know, when you look at something like Hurricane Sandy, we don't know yet whether or not climate change influenced the risk of that storm occurring, but we do know that whatever consequences there were piled on top of the sea level rise of about a foot over the last century, and almost certainly increased the damages that resulted from that storm. If you look into the future, the consequences of the changes in extremes are really pretty profound. I apologize for the complexity of this figure. Essentially what this is plotting is for 2 different periods in the future, the middle of the century and the end of the century, in 3 different climate scenarios, low amount of warming, medium, and a high amount of warming in the blue, green, and red. What is the future return interval of the 20-year most extreme heat wave? So if the bars are centered on 20, that means there's no change. If they're centered on 2, it means there's a 10-fold increase in the frequency of the 20-year hottest heat events. And what you can see is that if we look at the end of century period, which is the right-hand part of each bar, most of the bars are centered between 1 and 2, meaning that there's between a 10-fold and 20-fold increase in the probability of the 20-year most profound heat events. This kind of effect, really profound increase in the number of anticipated extremes, is very typical of what we know about high temperature events. It's less clear for the other kinds of extremes, but in general, all 4 of those extremes I talked about, heat, heavy precipitation, drought, and storm surge, have projections that show increases during the second half of the century. I want to spend just a couple of minutes closing on a map of the solution space. As I said, in many ways, this was the most interesting part of the project for me, and in many ways the most rewarding. And I think of the vulnerability exposure overlap as being a map of the problem space. And there are a whole bunch of different approaches that could be used in order to generate solutions. And they go all the way from investments in reducing vulnerability, sustainable development, things that are related to preparation, early warning systems, mechanisms like insurance that allow you to transfer and share risk, moving assets, reducing exposure so that so that the things are in places where they're not in harm's way, or really interesting kind of rethinking the way society works in order to have sustainable development grounded in mechanisms that reduce vulnerability and exposure. And what we tried to do in the report is say, okay, given what we know about climate science, how does that help us add the details to this map of the solution space? So we took every example that was played out in detail and we said, okay, what are the dimensions of the vulnerability and exposure? What can we say about climate extremes, not only at the global scale, but at the scale where real people on the ground would be doing real risk management? And then how do those play out in terms of risk management and adaptation? And what is striking and frustrating and entirely consistent with what I told you early in the presentation is that in general, the information on climate extremes, even when it's really good at the global scale, when we're talking about high heat events, it gets to be really challenging at the scale of risk management just because the climate change projections don't carry the details down to the level at which real disasters occur. And so when you think about how that translates into options for risk management and adaptation, the kinds of strategies that come forward as attractive tend to be the more general ones. So one of the case studies we looked at was the heat waves in Europe. As I already said, the 2003 heat wave resulted in tens of thousands of excess deaths. And we can say a lot about what the risk factors are, and we can say a few things about the projected changes in the climate drivers, and that the intersection between these results in a number of possible options for reducing risk, and that includes things like air-conditioned facilities, early warning systems, emphasis on developing social networks, and changes in urban infrastructure so that there's more opportunities for cooling. Many of these have been deployed in Europe, and the 2005 heat wave, which was comparable intensity to the 2003, resulted in a few hundred deaths as opposed to tens of thousands. Another example for which we had sufficient information to really look at all the aspects of the problem was hurricane risks along the Gulf Coast in the USA, where the projection is for a likely increase in maximum wind speed and associated heavy rainfall, although we can't say whether or not there will be changes in the number of hurricanes. And given this information, along with the risk factors, the kinds of risk management investments that make a difference include things like better forecasting, better warning systems, stricter building codes, and regional risk pooling, mechanisms that also help with sustainable development. So let me turn now to kind of the broad map of the dimensions of the solution space and reference that to the nature of the information that's available and the limitations on the information that's available. So the first conclusion that comes through in every analysis of the dimensions of the solution space is that a portfolio of actions is almost always better than an emphasis on any single action. And the portfolio of actions should take advantage of the fact that you can get benefits from emphasis on good communication, risk reduction, risk transfer, and emergency responses. A second set of general conclusions is that investments that pay off in terms of reducing risk of multiple kinds of hazards almost always yield higher benefits than investments that focus only on a single kind of hazard. And that applies not only to climate-related risks, but also to things that extend beyond the climate issues. A third general conclusion is that there isn't any actor in the risk reduction landscape that's really positioned to deal with the full range of issues. There are unique opportunities at the local scale, things like early warning system and enhanced social networks, but there are other kinds of unique opportunities at the scale of international organizations like large-scale emergency relief efforts or global-scale communication and early warning systems. And then a final set of conclusions is that even though we know quite a lot about building effective risk reduction strategies, we don't know anything close to what we need to be really effective, but we know enough to start. And the kinds of investments that are likely to pay off in the future are ones that can take advantage of an iterative approach where early investments allow us to learn about successes and failures, and where we can use that learning in order to generate a series of progressive improvements and really iterate our way out of the adaptation problem. That's what we learned from this, this special report, and I can really summarize it in a single slide. When you're trying to reduce risks of disasters, what you really want to do is find strategies that manage disaster risks now while also contributing to long-term well-being. Thanks very much for your attention.